Hey guys, I thought I'd have a quick screencast for one of the things that might show up on this AP. It's shown up the last couple of years, these two types of air bounds. So, uh, you know, I don't think it will, but we'll talk about it anyway, real quick. Okay, so suppose we have some alternating series. Okay, and I have the alternating harmonic series here, starting at 2. So I have a half minus a third plus a fourth minus a fifth, and so on. And we wanted to talk about our partial sum here, right? That's something that we've talked about here before, right? And so I don't know if you guys remember this, but we sort of use the notation. If I just took it the first 4 terms, we could call that S underscore 4, right? The fourth partial sum. And we can call the rest of this, everything else, the R4, right? Or the remainder here. The remainder, okay? Remainder, or we can also think of this as an error. And we'll sort of talk about that as the error of this whole sum. If I only look at the first 4 terms, right? The rest of it would sort of be the lost piece, right? The error. And we know that this thing converges, so we know that it converges to something. We just don't necessarily know what. So anyway, we're going to look at a bounds for this this remainder or this error here. And we're going to establish them so that we can talk about them on the AP. So if I wanted to rewrite this, I don't think any of you guys would have any problem with me saying, oh, look, this thing is really equal to the fourth partial sum plus this remainder, right? I'm obviously breaking it into 2 separate pieces. And we can readily calculate this fourth partial sum, right? This fourth partial sum is just a half minus a third plus a fourth minus a fifth. If you guys wanted to, you could do that with a common denominator maybe of 60. I think it's 30 over 60 minus 20 over 60 plus 15 over 60 minus 12 over 60. So what is that? That's 13 over 60. That's what those first 4 terms, and again, sorry if I'm making mistakes, but I think that's 13 over 60 is that fourth partial sum, right? So we could really say, okay, I have this 13 over 60, and then I have some leftover error, whatever this thing ultimately converges to. I know that this is 13 over 60 plus this remainder here. And we want to find an expression for that remainder. Well, we're going to have trouble actually knowing what that is, but we can find bounds for it. So we're looking at the fourth partial sum here, right? And we're looking at the remainder. So I'm going to divide this rest of this piece into two different ways. So first we're going to use blue. Okay, and I'm just going to draw parentheses around every pair of terms here, and maybe we'll list a couple more here just to better illustrate our point. Right, so maybe we have a 10th and a minus 11th and plus a 12th. Okay, so we can imagine that I have more parentheses here. And what can you tell me about every single blue term? Well, a 6th is bigger than a 7th, so this set here. Right, this set here is a positive number. We don't know what it is, but it's positive. Same thing here. 1/8 is bigger than a 9th. This is a positive number. 1/10 minus 1/11. This is a positive number. So my remainder R4, right, must be greater than 0. Why? Because it's the sum of all positive components, we'll say. Positive components, right? It's the sum of 1/6 minus a 7th, positive. 1/8 minus 1/9, positive. 1/10 minus 1/11, positive. It's all of those things are positive components. Well, let's now, hypothetically, so we've sort of established a lower bound, right? That the remainder or the error here after my fourth partial sum is greater than 0. Now, let's see if we can also rewrite this, and let's chunk this a slightly different way, okay? Let's try to establish a lower bound. So I'm actually going to come over here temporarily. Sorry if this bothers you guys. And I'm going to write this a little bit differently this time, right? So we're looking at the same set of remainders, blah, 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 okay? And now we're going to chunk it a little bit differently, okay? And what I'm going to do is I'm going to skip the first term, skip the first term. And then I'm going to draw parentheses here. And when I draw parentheses here, I'm going to have to change this sign. See if you can convince yourself of that, right? Because this eighth, it actually has to be positive, so we distribute the negative there. And then we would change this sign also. So we sort of have a whole bunch of negatives. Oops, I lost my little fraction bar. Okay. And what do we see here? Right? We see that if I rewrite my series this way, 1/7 minus 1/8, well, again, just like by my previous logic, this is a positive number. And this is a positive number. And the next one would be a positive number, right? If I just pair them off this way, sort of starting with the odd terms and subtracting the even terms, as opposed to the blue guys on the left, we'd be subtracting the odd terms from the even terms. Well, what can we say about this thing? Well, I know this R4, right, has to be less than a sixth. Why do I know that, right? Because I start with a sixth, and I'm subtracting positive numbers from it. I'm subtracting positive numbers, right? Because we subtract positive components from 1/6. So what does that tell us, right? What does that tell us? This is sort of my aside over here. That tells us that I have a bound for this fourth remainder for my partial sum, right? I have a bound of this remainder, and what it is it's between 0 and a sixth. What does that tell us? That tells us that if I have an alternating series, and I decide to sort of chunk it at any point, here I chose to block it off at 4, right? Here we said to block it off at 4. Well, that tells us that the sum of the rest of the terms can be no bigger than the next term, right? If I chunk it off at 4, the sum of the rest of the terms is sort of bounded by 1/6. It's bounded by 1/6, okay? Obviously, depending on where we chunk this, right, there could be something with absolute value here, right? If I brought it, if I talked about S, the fifth partial sum, right, then my things would be bounded by negative a seventh, not positive a seventh, negative a seventh, because the first term would be negative. So what this says is that after the next term, the rest of this stuff is sort of just noise that will make it smaller, right, make it closer to 0, and that 1/6 is really my upper bound of my error, right? 1/6 is the upper bound of my error, okay? So let's now look at a past AP problem, okay? Let's look at a past AP problem. This came from 2010, I think, 2010, okay? And where this is going to rear its head, it's only going to be a couple points, okay? It's going to talk to us something like this in part D. Something like this in part D, but this will be a good exercise for us to sort of review. Okay, so write the first 3 non-zero terms in the general term of the Taylor series for cos x about x equals 0, right? So that means a Maclaurin series about x equals 0. Okay, and what that means, right, is that we're going to be after something that we said we could memorize if we wanted to, but we don't necessarily have to, right? And so remember, for A, we're going to be looking at something that looks like we're going to want f of 0. Well, f is really cosine of x. If that's confusing to us, I'm sorry. So for f of x equals cos x, not this f up here. Maybe I should have used a different letter, but I didn't. Right, we're going to look at f of 0 plus f prime of 0 times x over 1 factorial plus f double prime of 0 times x squared over 2 factorial, dot, 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 dot. And for cosine, you guys can sort of figure this out on your own. I'm not going to do that right now. Right, we're going to start at 1, and then remember, for cosine sign, we skip every other term, right? So we're going to end up with x squared over 2 plus x to the 4th over 4 factorial. This is really 2 factorial. Minus x to the 6th over 6 factorial, dot, 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 dot. And, oops, I gave too many terms. I only asked for 3. Don't need this one. And right, we're gonna have all of this, and then my general term, right? Remember, they say they want the general term for oops, that's this one, general term for cosine x. Right, that's just gonna be we need a sort of an oscillator, so that's gonna be -1 to the n, right? Because we start with a positive number, right? So that we want that to be 0, and then we're gonna have x to the 2n over 2n factorial. You can verify that's what that is. That's sort of the general term. So that's the first part, and then the second part of A uses series to write the first 3 non-zero terms and the general term of the Taylor series for f about x equals 0. Okay, well this takes a little bit of thinking, right? Well, for f at 0, right, we're gonna have a little bit of different, right? So this is actually f, right? This is fake f. Fake f. Here's real f. Okay. So let's think about this. We have cosine of x minus 1 over x squared. Cosine of x minus 1 over x squared. Well, we want to sort of follow the same sort of rule, but we have this series already, and we're just sort of going to be dividing out x squareds as we move along. Okay, we're going to be dividing out x squareds as we move along. So my first term, right, is going to be f of 0. Well, that's just -1/2. -1/2. Okay, and then what's my next term? My next term is going to be each of these terms, we're going to have to subtract 1 and divide by x squared, right? So we're going to take the cosine thing here, we're going to subtract 1 and divide by x squared. So subtracting 1 from this guy, from this thing, sort of just eliminates this first term. And then dividing by x squared is just going to sort of make all of these terms smaller, right? It's going to make all of them smaller. Okay, so what that's going to end up with, right? What that's going to end up with is we're going to take away each of these terms, right? And we're gonna sort of reduce the degree up top by a little bit. We're gonna reduce the degree up top by a little bit. Okay, so what that's gonna look like? Hold on.